Recording is rolling. Welcome to Wednesday. We're going to do an Outwood lab. This paper is clipped to the front of your desk. You guys see a page that looks like this? So grab that one and I'll go over that with you guys, but let me get you guys into physics. Remind you guys what we've been doing for last week or so. You guys know that this homework set is due Friday. I have gone over these problems, so I bet most of you guys have already done these. Here's some bonus questions. If you do those and turn this in, then I'll give you some extra points. And you guys remember also AP Classroom Unit 2 multiple choice question progress check has been open for a while, and that's due Monday. Okay, so you guys got that? All right, so those are your assignments lined up. Let's do some warm-up stuff. Can you guys draw three body diagrams on each of the masses for each of these Atwood setups? There's the classic double elevator Atwood, and then there's the modified Atwood. So I'll take you guys over to answer this. I'm going to take each of these pictures and blow them up. So split this paper in half. Put the classic double elevator on the left side. Now this pulley, you guys are going to get these red pulleys today. They're very low friction, very small mass. So we're going to treat that as approximately frictionless and massless. Okay. And so double elevator, might want something like this, like maybe a large mass up here that I'll call mass A. And start off with a small mass down here. I'll call mass B. Okay. Can you make free body diagrams for each of those masses? So it's like a double free body diagram. Okay. So you guys have solved a problem that looks related to this in the last couple of days. The question was, at what rate does the system accelerate? And furthermore, what is the tension in the strain holding these together? Well, let's identify the forces, which is what we could kickstart this whole thing. So I know that mass A has a weight that I can call mg. Now I'll draw it really big because that's going to be the largest force vector. So I can call it mg. I will also throw a subscript A on that mass to say like mass A has that weight. Okay. Well, mass B also has a weight, but it's going to be much smaller, or something smaller. So I'll call it m sub b times g for that weight. Okay. Now, you guys remember that those two weights are the external forces that are driving the system. So the way to solve this problem on paper is to go to Newton's second law of motion, identify the net force, and the difference between these two ended up being the net force, kind of like two guys playing tug-of-war. Yeah. But there are other forces on the blocks. It isn't the tension force pulling each of these blocks upward. So let's put that here. Now, if you want to draw this correctly, I've been calling the tension force the Goldilocks force. The idea being that it's larger than the small weight, but less than the big weight. You see that? See how it's like the medium size force, right? Also, it's the same on both of the weights. I mean, if they're tied together by the same string, and this pulley up here is approximately massless and frictionless, then this string can only have one tension in it. So it's the same tension force applying to both blocks, pulling both upwards. But see how, because the tension force is the medium force, that the large block has a net force that's overall downwards because its weight is more than the tension. But the small weight, it's the opposite story. It has more force up than force down. Guess it? And because the net force on the big block is down and the net force on the small block is up, that means that it's going to accelerate that way, like down and up. And so this whole system will accelerate, looks like clockwise. Yes, yeah. Right. So that's for that one. Remember how this tension force is also internal to the system. So again, trying to apply Newton's second law of motion, looking at the system as a whole, like a macroscopic point of view, then tension is just an internal force. It's not actually driving the system, it's just holding everything together. Okay. But then later on, if you actually want to solve for that tension, remember how we did that is you just isolate one of the blocks. It could be either one. I did both in class too that works either way. And do Newton's second law as it would apply to one of the blocks individually. Okay. Then you could modify the Atwood machine to look like this, right? Where maybe it has like a horizontal type motion going on with it, where maybe one block is being pulled across a lab table and it's got a cliff drop, got a floor. Maybe throw in some hatch marks just to show that this is all solid right here. Okay. There's a pulley, massless, frictionless on the corner. I'm going to put a big old mass right here, and suppose this is seated on a Hot Wheels car. Right? I had it drawn here too. See that little Hot Wheels car? We won't get to this half of the lab until tomorrow, but when you do, why throw it on a Hot Wheels car? What's that about? Yeah, try to reduce the friction. Try to simulate a zero friction environment, which should be pretty close to. So I'll call this guy mass A and this guy mass B. And the same story, let's figure out what each of the free body diagrams looks like, one for each block. So I know that this mass A has a weight. I'll draw that downward. Call it M sub A times G. Right, that's the weight of block A. And so I'm not done with the block A yet, but I'll come back to it. What about block B? Now block B has, well, I made this block physically bigger, so that implies greater mass, greater weight. I bet it has a huge weight pulling down. Call it M sub B times G. So mg for block B. Okay, so now those are the weights of each of those blocks. So that's Earth's mass pulling on each of those blocks. So through gravitational field, it's called a field force. But hey, this one that's horizontal, is going to have horizontal motion. This block B up here on the lab table, doesn't it also have what kind of force acting on it, holding it up? Normal force. There's a normal force from the lab table holding it up. So I'll call it F sub n for normal force. But you guys know that that's equivalent to mg. It's the same magnitude, okay, because horizontal surface, nothing crazy going on. Okay. Okay. Those are all the external forces on each of those blocks. But if I look at this whole outlet system as a whole, like as a whole system, now there is tension in the strain, but it's just holding the blocks together, which I guess would be more forces on blocks too, right? But how large should you make the tension force? Should it be larger than or less than the weight of block A? It's always going to be less than. The tension is always going to be a bit less than the weight of block A. So I'll call that T. Okay? Because isn't it true, like no matter what you make these two blocks, you can make them pretty close to the same mass. You can put most mass up here, most mass down here. Regardless of what you make these masses, this thing's going to accelerate clockwise, isn't it? Right, clockwise. The boundary conditions would be if you have like 1 ton up here and like a paperclip down here, the acceleration would be pretty close to 0, and vice versa. If you put like 1 ton weight hanging down and like a paperclip up here, the acceleration would be extremely close to a perfect free fall. But either way, there has to be a net force downward on the one that's hanging down. But this tension, same story as before. If there's one string tying these together, then the same tension force is going to be over here. This tension, are the same magnitude. That's what I'm saying. Is it? Okay. So there's the complete free body diagrams on each of those blocks. Now, what's the resulting motion going to be? I see that the one that's hanging down has a net force. That's the difference of those two forces. And I see that the block on the table, hey, what happens to the two vertical forces? They do cancel. So that is not even going to drive the block to move. If I put more and more mass up here, if I make mass B bigger, 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 will that slow down the acceleration of the system? How many of you guys say it will? More mass up here is going to slow down the acceleration of the system. Yeah, you're right. It would, because that would create more and more inertia that this whole system has moved. Right now, the weight, you guys see this weight down here? The weight of block A, that is the only net force that's driving the system to move. So if you go to Newton's second law of motion, you just solve it on paper that way, then this would be the net external force driving the entire system to move. Tension, again, is just holding the system all together. Right. Now, the weight of this block up here cancels out. So the force doesn't really matter so much, but it does have inertia. Right? The more mass up here, the more inertia has to be moved by this single weight force. Is that? Now, you can go through and solve for the acceleration of the system just on paper, and we've done a bit of that last couple days. But today, you guys are going to get to do the science version of this. That's to say, go to the lab, make some measurements, do some calculations, and see how this works out. So here's the classic double elevator setup. Here's the modified version. It has a horizontal component on it. Today, you guys will have time to do the left side, and tomorrow, you guys will have time to do the right side. Let's scroll down to the bottom of this page to see what is the ultimate goal of this lab. The ultimate goal, it says, find a relationship among acceleration of the system, free fall gravity, and mass 1 and mass 2, each of the masses. find an expression that would tie all this together. And I started out for you guys. I said acceleration is equal to, and there's going to be some expression here, which is just going to be in terms of variables. So the answer to this lab, this is true for both parts, will have no numbers in it. It's just going to be in terms of variables. So each of the masses in pure free fall. How are you going to get that? Well, two ways to get it. One way is you could solve it on paper with Newton's second law of motion, like we've been doing the last couple of days. The other way is to go through this table and make a bunch of measurements one at a time. So how to read this table? Notice that I've swapped out kilograms and meters with grams and centimeters. You guys see that? So be ready to field that. It's probably more practical for the size weights that you guys have here today. G is 980? What's that about? 980 centimeters per second squared. Isn't that 9.8 meters per second squared? So this represents pure free fall. Those would be different on different planets, but we're all on Earth today. Anyway, mass 1, mass 2, record those in grams. The largest slab weight back there is 1,000 grams. Okay, that's the 1 kilogram mass. I want you to take the difference of those two and the sum of those two. And then the difference, I said absolute value, so I care about the magnitude of the difference. That's to say that ultimately I don't care if this is going counterclockwise or clockwise, I just care about the magnitude of the acceleration that comes out of it. So something to do with the difference, something to do with the sum. Okay? X in centimeters. So how far has the system moved? And then T time, you're going to time. You guys brought your cell phones today, right? I'm sure just for this lab, sure you woke up to that. Oh, I'm going to have a different lab. I'm going to use a stopwatch function. So, good thing you guys brought your cell phones. You guys are going to time. How long does it take to move some distance? So here's something I mocked up earlier. Say you start with a heavy weight up here and the light weight down here, and these two are going to change places. So whatever this distance is, the starting distance, this distance that they're going to exchange places, that is the value X. Record some number of centimeters. You guys see the longer string you use, the easier it's going to be to time. Like if this is at least a meter long, then that'd probably be pretty easy to time. If it's like 20 centimeters long, it's going to go just like super fast and that'd be kind of hard to do. Okay? So that's one tidbit is, well, if you use a pretty long string, at least a meter long, that'll help you out. Another tidbit is, you guys remember we've been playing around, at least like textbook values, with boundary conditions. Think about these masses. If these masses were exactly the same, like 200 grams, what would that system do? It would just not accelerate at all. What if you put all the weight on one side? You have perfect free fall. Right, so this acceleration system is going to be somewhere between those two boundary conditions. But which one do you think is easier to time in a practical lab sense? Probably if they're pretty close to each other. Right? So that's why I did like 200 grams, and then you can actually tag on another lab mass to just notch up one a little bit compared to the other. So I'm giving you guys a tip here. Right, that'll show up on the video too, because otherwise normally I just let you guys figure it out yourselves, but you should watch this in the video in the future. All right. How are we finishing off this table? So we know there's going to be some exchange distance. There's going to be some time. Oh, look, 3 times to take an average. That's a pretty common thing that we do in this class and that you would want to mention explicitly on your AP FRQ write-up when they ask for experimental design in May. Do like multiple trials, take an average. Okay. And then this last column, acceleration. Now this is going to be a calculated acceleration based on, well, if you can keep a track, you would actually have 3 kinematic values at this point. The system starts from rest, initial velocity 0. It moves some exchange distance, x, and so much time. That's 3 kinematic values, isn't it? And you can use that to calculate acceleration. You guys remember this equation right here? X equals 1/2 at squared. Oh, isn't that the college equation? Oh, there's the mine shaft. Oh, but 125 meters. This is the one he was using, isn't it? You can rearrange it and solve for A. I did that work for you guys. I shouldn't have you guys for AP, but I had 1 lab paper, so that's what you guys got printed. You guys can calculate what the acceleration should be. And remember, what's the smallest value that this could possibly be? 0. And what's the largest value this could possibly be? Yeah, 9.8 meters per second squared, or 980 centimeters per second squared if you're using centimeters, right? So one more thing to help you guys out. You see how some of these columns have stars at the bottom? So that's pure free fall, the difference of the masses, the sum of the masses, and the calculated acceleration. Right? There's some way that you can multiply or divide the first 3 columns that should land you pretty consistently numbers that are pretty close to the calculated acceleration. So help you guys out quite a bit here, and if you pay real close attention to your notes from the last couple of days, you actually might have this answer maybe. Okay? And then similar story tomorrow. Now the setup's a little different, but similar idea. So your answer, it will not have any numbers in it. It's just going to be an expression in terms of variables. What is the general acceleration of any outward based on the two input masses and the free fall gravity of the planet? Any questions so far? All right. So you guys got all lab materials you need back there, and I will walk around and help you guys out.